I'll pass it over to her.
Okay, so my name is Matt Heitzenroder, as you mentioned. I'm from Basho Technologies. How many people here are familiar with Basho and Riak? Anybody not heard about us?
I've heard just a little bit about Riak.
Okay, great.
I heard y'all were like the undisputed king of like NoSQL.
Yes, absolutely. You've heard correctly. So Travis invited me here today, so thank you, Travis, for bringing me here. I'm in from Miami. I figured I'd start off today by telling you a little bit of a story about what it took for me to get here. When I arrived at my gate, the plane was delayed by an hour because some delaminated window in the plane, which I guess compromised cabin pressure, required some repair. And so as we waited, eventually the plane was fixed and they boarded everybody, and I'm starting to get a little bit nervous about getting here on time. And as we're sitting there, the next thing that comes over the speaker is that the plane is full of shit. Literally, it's full of shit. Like they couldn't take off because the labs weren't available to be used. Like the heads of the plane weren't available to be used because the tanks were full. So they called the poop sucking truck over to the plane, and the poop pumper came over and was supposed to do its sucking job, but apparently the poop pumper was also full, so it had to go back and then discharge. This is the way we do things in Miami. And then discharge its waste. And by that time, it was like, oh, a whole another hour. I imagine they probably had to dump 30,000 gallons of waste or something from a truck. I don't know exactly what happened.
Could have just dumped it on the way.
I'm sure it wouldn't have really made a difference. Yeah, it came back and got us underway, and I basically missed my connecting flight in Dallas, but I made it here on time. And I think it's kind of suiting for today because I think one of the major topics that I'm going to try to hit on is that shit happens, and you want to remain available. I'm really happy that I could actually make it here and be available for this. So I just thought it was a suiting story to share with you guys about what it took to get here. So my name is Matt, like I said. I'm technical account manager, and I've been engaged with Basho for the last 2 years and been working with them for almost a year now. And I've kind of been a part of Riak from the beginning, so I figured I'd be able to probably aim this talk kind of at the hello, I'm going to introduce you to Riak and some of the ideas that built the product. Probably for the data stacks guys, it's not going to be very enthralling. So it's pretty much the same story you guys already know. So what is it? For those of you who are just here for the pizza and got to get home to your families and got to go back to work, basically I like to think that it's web scale. So that's it. End of story. That's all you really needed to know. You can go home now. For those of you who I guess are going to stay and want a little bit more than that, prepare for the buzzwords, okay? Riak is a highly available, linearly scalable, fault-tolerant, Dynamo-inspired, open-source, web-oriented, key-value, plus goodies data store. And basically, what that really means to us, because that's a mouthful to say all the time, is that it is the data store that the Akamai DevOps team always wanted. So if you're confused of why I'm mentioning Akamai at this point and what the DevOps team has to do with Basho and Riak, I got to tell you a little bit about Basho. Back in 2008, Basho was founded by a bunch of people who defected from Akamai, the execs and the DevOps team to be specific. And that team was inspired enough or was compelled enough to go solve a problem that they had been dealing with for a long time, and really just wanted to build the database that they wanted for their operations center. So they basically set up shop in Cambridge, and the rest is history so far, which is not much of a history. It's been about 2 years. And we opened up an office in San Francisco maybe a year ago. Reston maybe 2 weeks ago, and a whole bunch of us are remote, including myself. And we're about 30-ish people. We got people in the UK and Germany, and you know, I guess as far west as California. So if you guys are interested in hacking on some Erlang databases and Dynamo databases, if this intrigues you, or we have a whole bunch of positions open, let me know. Anyhow, this problem that these DevOps teams guys really wanted to solve was basically low latency at scale, getting your data to low latency at scale. And frankly, in my opinion, low latency data at scale is the problem. It's not uptime, like a lot of people think. Like, oh, I have an SLA of 99 and 5/9 uptime. Well, I mean, basically, I could be up, have uptime for my database running at like 100%, but if I don't respond to requests or I don't service requests, in a reasonable amount of time, it's effectively down. So these guys, their goal is to basically make data get to you as fast as possible and do it at scale, at a global scale. Remember, it's a CDN that they had come from. So probably the number one thought that really came across their mind while they were dealing with this is that data should be available even under failure conditions. So if you basically have a failure condition and it prevents a request from being serviced, you're effectively, data is ultimately indefinitely latent. So, you can kind of put these pieces together, and one of the most inspiring things for Basho was a paper that Amazon wrote in 2007, Werner Vogel's and his team called the Amazon Dynamo paper. How many people are familiar with Dynamo? So there's what? I'm sorry, you guys are like this. Yeah. So it's like really hard to figure out. Okay, all right, so it's like half. So let me tell you guys a little bit about Dynamo. This is just basically a small primer. I'm hardly not doing it justice, but it's a really accessible academic paper on distributed systems and data storage. And Dynamo is basically what a distributed system data store that Amazon created for basically their 99.9% users, who are the ones who buy a lot of shit and use it all the time. They do want to stop those people from buying stuff. And they wanted to make sure that the shopping cart was cool and going and blah, 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 blah. So their main goal was to have a system that they could scale simply, they could scale it predictably, and make sure that they provide data available at all times as their high-end users or their power users are shopping. Dynamo is not S3, but it does back S3, or at least has some part of its infrastructure involved with it. And the Dynamo paper goes on to describe how to configure a bunch of nodes to work in concert together, so that through this idea of consistent hashing and some other anti-entropy algorithms, it kind of takes all these algorithms from the past 30 years in computer science, throws them together to kind of say, this is a new way that we want to store data. And it's a decentralized, distributed database that is eventually consistent. And frankly, the eventual consistency usually gets people kind of hung up when they're just coming over from maybe the SQL data stores of yesteryear. And it's been a couple years, NoSQL's been around now, and hopefully the idea of eventual consistency is kind of setting in to people's minds at this point. But if it isn't, I'm going to walk you through it. Dynamo basically chooses data availability over data consistency. And so the key part of that statement is that they choose, that there's a trade-off. And the trade-off that they're talking about, because they can't have consistency and availability at the same time, they have to choose it. This trade-off is known as the Cap Theorem. And the Cap Theorem was actually presented originally by Eric Brewer, who's the VP of, now he's the VP of infrastructure at Google. And in 2000, he presented it at the ACM at the Principles of Distributed Systems. Basically, he was the keynote, and he put forth this conjecture that in a distributed system, we want 3 properties all the time. And that's consistency, availability, and partition tolerance. So basically, I have this distributed system. It's my data storage. And I want it to be consistent, I want it to be available, and I want it to be able to be partition tolerant. But his conjecture says you only get to pick 2. It's an iron triangle. You want all 3, but you can only have 2. So which ones are it? Or which one is it going to be? Which 2 are it going to be? So first of all, I think it's probably worth a conversation to walk through and say, what are these 3 things, just so that we're all on the same page. And a few years later, a pair of academics called Gilbert and Lynch went on to go on and prove this theorem, this conjecture, Brewer's conjecture, and created the Cap Theorem. But they went on to say consistency in a distributed system is basically this. Whenever I write or I read data from the system, like no matter what, it's going to be the same in the exact same moment, right now. Like, doesn't matter which 2 nodes, 3 nodes, 4 nodes I talk to, the data is always going to be the same, and I'm asking in the exact same moment. So consistency, it's fairly easy. I'm sure you guys kind of got your mind wrapped around it. We've been doing this for decades, right? We get consistency. So availability, we also get availability because we always want our data to be available, right? And basically what Gilbert and Lynch define availability as is the ability for a node to fail and any other node in this distributed system to be able to respond to requests. And so if a node drops off, look, like no big deal, any other node in this distributed system is available to respond and provide the request to the response. This is the one that I think is always tricky, partition tolerance. And a few other people have commented on this out in like the interwebs as well. But basically, partition tolerance is what it sounds like, in my opinion. It's like the network in between is what basically, I just noticed I'm missing my notes. Damn. Basically, the network in between, if it can be severed, we need to be able to withstand that. And basically, the way I see it is that a distributed system implies partitions. Partitions imply a network, and a network implies failure. So like, we don't live in a perfect world. Networks fail, packets drop, sunspots happen, right? So you don't have a choice when you go to build a distributed system that's going to store your data for partition tolerance. You have to have it. You don't get a choice. If you're going to have a distributed system, you have to have a partition-tolerant distributed system. We don't live in a world, as Coda Hale from Yammer points out, we don't live in a world where perfect networks where UDP packets are going to be delivered or TCP packets are going to be delivered guaranteed. Just not really going to happen. So this actually brings me to a pro tip. If you're evaluating a distributed system and that system happens to claim that they are consistent and available, turn around, run away, right away, because they don't know what they're talking about. You cannot be consistent and available at the exact same time, because there is going, in a distributed system, mind you, that's what I'm talking about, distributed systems. So the real trade-off that we have to deal with is consistency and partition tolerance and availability and partition tolerance. So you get one of those choices, right? And Amazon chose availability and partition tolerance for their distributed system in Dynamo. You guys with me so far? All right, cool. Let me break it down. I have a really simple, a lot of this is nice and really academic and fun, I guess, to like mentally masturbate over, but like, it's a lot easier to imagine it in real world terms. And I think banks are a good example of this. Banks have been dealing with eventual consistency for longer than eventual consistency has been a term, right? Much longer than probably like computers have been a term, I don't know. They have headquarters, right? And you and I, at least I don't know about you guys, but I don't go to my bank headquarters. Can you guys see that? Can you put the lights? Is that possible? That's good, I guess, yeah. I just want to make sure that my slides are visible. Can you guys see it back there? All right, it's just a bank. So basically, I don't go to my bank headquarters every time I need to get money out of my account. That's inconvenient. So these guys, thankfully, you can't see this either, but this is a row of ATM machines, and they make my life way more convenient, which is great, because I can go and get my money anytime I want. Even though my account, this central book of record in this distributed system, it's a centralized distributed system, mind you, because there's a central record, but it's a distributed system. I'm able to go get my money from an ATM at any time without having to go to the headquarters, which is great. So it all works in this beautiful little principle, like the cloud, right? Of course. And everything is good until the inevitable backhoe. And once that backhoe happens, the banks are faced with a dilemma, right? Their dilemma is, should we keep our accounts consistent and not allow this guy to get his money? Or do we make the money available to him and we figure it out later? That's their choice. That's the dilemma. In my opinion, the dilemma, that's not the dilemma. The dilemma really is, what's the best user experience, right? Should you screw me out of my money? Or should, I'm sorry, I had it backwards. Should I be able to get my money? Or should you screw me out of it?
It's a bank. What do you think's going to happen?
And they've come up with all sorts of interesting ways of dealing with this. Like, you know, you can only get $200 out at this time, you know? So, like, they've been dealing with eventual consistency for a very long time. And frankly, I like it when they give me my money, because it's my money, right? So, you know, basically, what I'm saying is that you have this partitioned network, this split brain, right? These two individual systems, and I can either keep the records consistent and not allow a transaction, you know, or I can give the person their money and I can reconcile it later. These are the trade-offs. The way that I see it is that it's either eventually available or eventually consistent. And I think eventually usually means now, in a little bit, or later, or never. So you just have to think of those terms, and that's the low latency data problem that we're talking about. Okay, so meanwhile, back at Basho, trying to solve this low latency data problem. Riak begins to take shape. And the shape that it takes is a ring, right? And this ring is basically outlined or described by Dynamo, the Dynamo paper by Amazon in 2007. And it basically says, hey, we're going to take a 160-bit integer, we're going to partition that up, distribute it amongst some physical nodes, and they're going to take this ownership of it, and we're going to use consistent hashing in order to say this is where you own parts of the ring, or data locality on parts of the ring. So as you can see here, I have nice little color-coded nodes. These are my physical nodes. This is my 160-bit hash ring, and I've divided it up into 32 partitions. So my 4 nodes have divided these 32 partitions up, and this is basically my key space. So, okay, it's getting, it's starting to take shape. Let me think, what else? These basically are virtual nodes. You'll hear us say at Riak or at Basho, we'll call these virtual nodes or partitions. We use the words interchangeably. And this is actually what maintains the records of data. It actually gives us the high availability that we're looking for. So like whenever I do some kind of like write operation, basically I'm going to hash it and it's going to tell me, oh, I'm going to go to like this partition, and this partition, which belong to these, to these physical nodes. Because what I'm doing is I'm actually creating 3 replicas of the data. So now I have high availability. I can actually lose a node. Something bad happens to my green nodes, right? We can cross out all my green nodes. But I have 3 replicas, so I'm able to get at least from the orange and the magenta, I guess, pink, back fuchsia. No, fuchsia. I don't know. Anyhow. So I'm able to get the data back. So that's basically how it works. That's kind of the science behind it. So this is the ideas behind Riak. What do devs get from Riak? They basically get a key value store. The key value is a simple API with your general operations, get, put, delete. It's content agnostic. Remember, these guys came from a CDN. They didn't care what they stored. We can store binary data. We can store serialized JSON, XML, whatever. It doesn't matter. We don't care what the data is. We just want to store it. We have object namespacing, what we call buckets. And if you can think about it like little 5-gallon buckets, it allows you to just drop objects in at will wherever you want so that you have a logical separator between them. And then we always give it a little bit of metadata as well. And that metadata will give it, I'll describe it a little bit more. One of the other features that we give devs are cap controls. And this is a tweet that I read out on the internet that I thought was really funny, so I had to include it. It was basically less BS, more CS plus tunable cap controls. I thought it was pretty funny. So what do I mean by cap controls? You can control the availability or the level of inconsistency that you want. So whenever I say like do a read, so the R value, and I want 2 nodes reporting back to me, I'm able to specify, make sure that 2 nodes report back to me. So I do this get, these 3 nodes, this coordinating node, this green one, whatever, is going to coordinate the request. It's going to send it off to these 3 in the ring. And then the pink fuchsia one is down again, which is terrible. No, maybe it was the green one before. Anyhow, pink fuchsia, green one, or pink fuchsia is down, and then the green and the orange are able to respond to the request at this point because it satisfies the requirement of R that I requested. So with an R value, I can say, hey, make sure that 2 nodes are up. That's enough consistency for me to service the response and say, hey, I'll give it back to my user. And same holds true for the W value, which basically says guarantee me that these many nodes are up and online whenever I do a write. So again, I do a write, it gets hashed. My N value, which specifies the number of replicas that I want to store in my cluster, goes there, goes to write 3. This time it's the green one that's down. I have a terrible ops team. This time the green one's down, and then I have these other 2 that are up. They're able to accept the write. They okay it. They say we got it, and then there we go. The write was accepted. So you can get really paranoid, and you can do something like n equals 10. So you want 10 replicas of the data. So whenever I do any type of write, all write operation, it's going to write out 10 replicas of the data across the ring. That pretty much gives me a lot of flexibility. I can lose several nodes and still be pretty cool. It also really begins to put some bounds on my capacity in my cluster as well. Got to keep that in consideration. Life's full of trade-offs, So in this case, though, we have an R value and a W value of 2, which means when I do any type of read or write operations on this data, that I've already specified that as long as 2 nodes or 2 partitions report back to me and say, hey, I'm up and I'm servicing requests, and they give me back the data, it's cool by me. It's enough consistency for me. So what else do devs get? They get object version control. The best way to describe this, and I'll walk through this in a minute, but the best way to describe object version control is something called vector clocks. And it's basically, or the feature is vector clocks, and it's a logical timestamp. I like to think of vector clocks as basically a get commit hash. It's not an actual timestamp, it's a logical timestamp of when things happen in the distributed system relative to each other. So it's basically version control, right? And the reason why it is that way, I don't know about you guys, but I can't even get my microwave and my oven in the same room with like a resolution of a minute to be on time so that they change in between, and I tried like hell. right, to get these things in sync, and they don't happen. And I'm sure as hell not going to get something with a resolution of microseconds to be in sync when I'm trying to get like, I don't know, 8 physical nodes, 12 physical nodes, 30 physical nodes, whatever, plus all the clients talking the same wall clock time. Not possible. So we've got to use some other kind of logical time stamping. That's vector clocks. And it basically gives the data object, that object metadata, a version number. So this is in, like, here's my ring, right? We zoomed in. We're looking basically at the anatomy of a request right now. And so here I am. I'm going to do a get operation from my client. And in this case, I'm requesting r equals 2. I want to make sure that at least 2 partitions report back with an answer to my question for data. And so what happens here is that the get handler goes out and sends a request to the 3 nodes that are responsible for it. It knows which nodes to go to because it uses consistent hashing. And these requests come. 11 is out, pesky pink. And it doesn't send a response, but 10 and 12 do. And when 10 and 12 respond, 12 sends back version 2, 10 sends back version 1. And what just happened here was that we had a descendant of an ancestor in data. And Riak says, oh, okay, that's cool, not a problem. Obviously this one is a descendant, so it's newer. So basically it's a commit after, right? It's easy enough. And so I'm just going to respond with v2. But I'm also going to do an operation that Dynamo specifies called read repair. And I'm going to tell 10, who gave me the old one, that there's an updated version. So voila. Now I'm eventually consistent. Eventually, I became consistent. And if I do a write operation on this and 11 is still down for some reason, it will go through the exact same process.
Is that the only way that 11 would ever get caught up? Or?
When it comes back online?
Yeah.
Yeah, otherwise it's offline.
Well, there's a couple of other mechanisms for making them.
Yeah, when it comes back online, is it smart enough to go sync itself up, and that's what I'm saying? Or does it wait until new data is pushed down back onto it?
That's part of handoff, I believe, right? So whenever it comes back on and it starts servicing requests again, it will take care of all of that.
Basically, another node stores the writes until the node comes back up and then replays them.
All right, so what else did they get? Developers, you guys get a web-shaped API. Riak is also considered to be web-oriented. We have an HTTP layer. It's our default interface, but it's not the only one. We think that it does REST really well. If you guys have ever seen or heard about Web Machine, it's a RESTful framework for writing RESTful applications in Erlang. And it's basically the backbone of our API. The nice thing about this is that Riak plays really well with any HTTP infrastructure. So if you want to do something like, say, put varnish on all of your nodes in the cluster, then your reads can be stored in varnish, and then you could, expire the cache whenever you need to. So basically, then you don't have to go through the whole process of getting getting the ring, or going across the ring and across for requests. You can service requests much faster if that's the case, if you so choose. And it makes it very suitable for many other applications, or web applications. We also make a binary API available. It's called, if you guys are familiar with Google's protocol buffers, it's an implementation for that. It's fast, which is good. It's a persistent connection, which is good. But it is less robust than HTTP. So again, trade-offs. You don't get as much functionality and metadata that you get out of HTTP, which is a nice, rich protocol. But you do get a much faster API.
What would be an example for you to use the protobufs over the HTTP?
It depends on what your latency requirements are.
Is it strictly around speed?
Yeah, usually it's strictly around speed. Latency and throughput. Those are like, what are you trying to get from your cluster? And it also depends on like what's your writes versus your reads. you know, I was mentioning Varnish earlier. One of the implementations that I kind of think is sexy is you're doing all your writes with protocol buffers and doing all your reads over HTTP and have something with Varnish in front of it. So if you can handle that kind of setup, I think it's a pretty good one. We also give developers MapReduce. I don't know if you guys have ever seen this cartoon, but basically it says, hey, how do I query my database? You write a MapReduce function in Erlang. Did you just tell me to go fuck myself? I believe I did, Bob. Right? That's pretty much it. Like, we provide JavaScript and Erlang to query the database. It's not a type of query mechanism that you would go out to like Hadoop with. It's not for huge batch jobs or anything like that. It's much more suited for ad hoc queries. And there's actually a lot of development going around our MapReduce framework right now so that it can become more like Hadoop style. We have a bunch of client APIs, of course, so pick your favorite language. There's some pretty robust ones. Brett back there just committed to the Python one. Thank you, Brett. The Java one has gone from like 0 to 60 in the last 6 months. It's pretty sexy now for Java. JavaScript's been around for a while and pretty stable. Our Ruby client API is solid. It's really nice. Maintained by Sean Cribbs, who's part of our support team. And of course, the Erlang is just dandy. The other ones, the Haskell one is pretty good. The .NET is pretty new. We'll see how that one develops. PHP is HTTP only, no protocol buffers implementation. Perl, I don't know much about. And the C is actually quickly developing as well, as we got some clients who are using various C applications, and so that's getting to become more robust. The other thing that we offer is a pluggable storage backend. And basically what this is how we handle operations to disk or even into memory. We have our preferred backend, which we baked ourselves, which is called Bitcast. It's super sweet, super fast, it's predictable. You never do more than one seek, but the trade-off is that all your keys have to fit into memory, at least for that physical node. So just to give you an example, the overhead of a key might be about 44 bytes. If you have an 8 gig machine, you can fit about 250 million keys in 8 gigs of RAM. Doesn't store the values in RAM. It just stores a pointer from the key to the value. It's an append-only log file that gets merges frequently, but in downtime. So like if and you can schedule these merges as well. So basically, it's really fast. It's very predictable, and we like it quite a bit. But if you have billions and billions and billions of keys, that's a different story. You need some alternatives. That's where InnoStore comes in, and it's trusty old InnoDB. And basically, you don't have the same issues or the same in-memory requirements, but the trade-off is that it's not as fast. We like to think that it's a pain in the ass to tune, and it's not really known for its fault tolerance. So like it gets corrupted every once in a while. It's a pain in the ass. We're really excited because in our forthcoming release, we're going to be releasing a level DB backend, which is Google's new KeyValue store. They basically use it in Chrome. And it's kind of like Bitcast, except that it doesn't put stuff it doesn't put the keys in memory. It does it similar to InnoStore and does pagination and whatnot for that. But it's still wicked fast, and it's still an append-only log file. And so we think that it has better recovery options than, say, InnoStore. So we're really looking forward to Level DB. There's a bunch more other little features that I'm not going to go into, but I'll just cursorily run over them. We have pre and post commit hooks, so if you want to do something fancy with your data, or like you want to do some kind of operation before or after. We have large object chunking. The best way to describe that is if you have like a 100 megabyte or 200 megabyte video file or something and you want to store it in the database, we can totally do that. What we'll do is we'll break it up into chunks that you specify a block size for, send it over the cluster, and then whenever you make a request for that key that you stored it under, it'll be able to pull it out and pull all these chunks together. And each one of those chunks are treated as individual objects, So basically, they're subject to the like n equals 3. If I want 3 replicas, then each chunk is replicated 3 times. So it's really nice. It really allows for quick storage and retrieval.
What do you guys consider a large object? Like, what's the
15 megabytes is what I usually tell people, but really the answer is it's your level for latency, because what happens is those partitions on the ring, all those little colored or all the little sections on the ring, not the colors, but the sections. Basically, what happens is it's a blocking request to do a read off of the disk, and so when you have a large file, you're blocking that partition for a while, and you're basically causing latency on your request. So how much latency can you tolerate is really the answer. If you can handle latency forever, which I actually know some people can, they don't really care. They don't need to use LUOC, although they're still interested in it. But a lot of times I think about 50 megabytes, and then you start really starting to feel the pain.
Did you say reads are blocking per vnode?
Yeah.
Is it per physical node or just per vnode?
Per vnode. So
typically, how many vNodes do you have per node?
we usually recommend like 10 to 20. So it really depends on what you're trying to do. You know, by default, like what I tend to tell people is to not change anything. And the default ring size is 64 partitions. And we usually say, you know, you can do pretty well with a 4-node cluster if your throughput's, you know, like starting level. In a 4-node cluster, you get 16 partitions per physical node. We have another feature that's called links, and it basically creates an object relational graph. Oh, I'm sorry, Brett, did you have a question?
I was going to ask the exact same thing, but I guess the follow-up for me, and maybe it's too specific, but you said you recommend 10 to 20 per vnode.
That's usually
like,
what
when I talked to
recommend.
Andy, he just said it doesn't really matter, there's no upper limit, so we have like 400, because who cares? Is there
An upper limit per vnode or
per physical host, the total ring size? Like, we basically didn't want to be stuck at 64 in 2 years.
So what's your ring size?
We did 1024 with the start of like 4 hosts.
So here's the thing. Every time you do another partition, and I'm surprised Andy responded this way. I wonder if he was drunk. No, I'm just kidding.
well, yeah, I think we both were, so.
Okay. So basically, per partition, what we do in Erlang in the VM is we spin up a PID for a process, an Erlang process for each one. So there's an expense for each one of those PIDs per partition. So every node that you run, physical node, you're spinning up 1024 processes, and it starts to eat up the.
You mean OS PID or Erlang PID?
Erlang PID.
Well, I mean, 1024 Erlang PIDs, isn't that like nothing?
It's minimal, but you don't, I mean, like, you want to be, like, somewhat conservative. I mean, you don't want to just spawn the world, right?
Sure.
Like,
Brett does.
Yeah, I do. Okay.
It's a big world spawner.
4,096 children. Sorry.
All right, I mean, I'll look into it. It's
Is it easy to resplit the
Resize the ring?
Yeah.
Or if you,
maybe not easy, but possible.
it is possible, it's not easy. Resizing the ring is kind of a pain in the ass, but like, I mean, obviously adding and subtracting physical nodes is not a big deal.
Right.
So you really want to try to like figure out exactly how many partitions your ring size should be that you can grow into reasonably without like burdening your system. I mean, 1024 is not unheard of, right? And depending on how much you guys are going to be using and what your requirements are or how large your cluster is, that might make total sense. We have, as you now know, like implementations that are 1024 and larger. That's a larger ring size for us. A lot of times, like you can do pretty well with 512. Did I answer your question?
Yeah.
So going back here, was there any other questions? That was a good couple questions. Going back to some of the other features, we have this object relational graphing feature. Basically, if you think of each document that you're storing in the KeyValue store, each value, and you think about it as like a web page, right? And you think of that web page with a link that points to another web page. That's basically what links are, hence the name links. So what we allow is you to traverse that relationships in a single request and be able to aggregate and pull back the responses.
Is that the metadata? Because you said you were content.
Yeah, that's part of the metadata. So the vector clocks and the link stuff, if you want to add that, are all part of the metadata, the object's metadata.
Are those links one way or two way?
They're one way. If you want to do two-way, you just link back to the other direction. And actually, if you're a Ruby programmer, like Ripple does a really nice job of doing that, which is the Ruby library I mentioned earlier. We also have a separate project, not for long, that does full text indexing and search. It's called React Search. It's still React, but it provides like a Solar API, and basically it's a distributed full text search engine. It's not Google in a box, so don't go crazy. But it's definitely in use in large companies. It's been road tested. It's one of our beta projects, but we're actually merging it back into the core product. It'll be there by default. It'll be turned off by default, but if you want full text search in your data store, you'll be able to do it. So that's pretty cool.
What are the trade-offs there? Like, if I want to enable indexing and all that sort of thing, is there like a, I don't know.
It really depends on how much you're indexing and how large your data set is, how many responses you're expecting to get back. It's term-based partitioning. So the real trade-off, the best way to break down the real trade-offs for React Search is you get distributed search, or a distributed search cluster, which is pretty badass. But the actual indexing takes about 1.5 times longer, or maybe about 2 times longer from what you're used to with something like Solar. And the indexes are about 1.5 times larger, but the querying is super fast and predictably scalable. So those are the trade-offs. Solar does a better job, and actually we do have a Solar API and we have a MapReduce API, HTTP API. These things are good, but they're not as robust as Solar. Like, we don't have facets and stuff like that. But again, you get a distributed search cluster. And it's something that we're going to continue to develop because that horse is out of the stable. So people are using it, and so we're supporting it. So this basically breaks down what React looks like from an architectural standpoint, like a single actual node, a running instance of React. All the things I kind of talked about from top to bottom are your APIs. Here's all the Dynamo bits. You'll hear a lot of us talk about React Core, which is an open source framework that basically allows you to do this whole ring business and generate your apps. So if you want to create your own Dynamo apps, you basically can do that with React Core, which is pretty exciting. It's the proof of concept for React Core was React Search. And so this is an abstraction that's open source and available. We're a really open source company, by the way. Like most of our stuff is open source. And I've talked a lot about the vnode master. We have our KeyValue vnodes, and then our actual storage backends for storing the disk. Okay, so I said our DevOps team, right? And so like one of our goals is to make ops life super, super easy. And the way that we do that is we make scaling trivial. This is what it takes to scale a cluster. You just got to issue a React admin join, tell it to about one of the nodes in the cluster, and you'll bring a new node online. All the partition transfer takes place. The ring claim ownership takes place automatically. It's all done for you. That's it. That's how you expand your cluster. And it's also just as trivial to scale down. It's not, you don't have to go and think about it. You just issue another command, React admin leave, and the node will begin to do partition transfer, and it will then exit from the cluster. So super easy. That doesn't mean, you wouldn't believe how much this happens, but a lot of people think, oh, that's great. I'll just like have some, what are those AWS instances that are super spotty? Like, the micros? Not even the micro ones, like the ones that you can bid on.
Spot pricing.
Okay, right. They just disappear rapidly, so like people think, oh, I'll make my cluster out of those and it'll be super cheap. bad idea. Like, you know, and oh, I want to be able to just dynamically grow to 100 nodes from 3, like in the next 5 minutes. Go. I think actually that's where Cassandra kicks our ass. Like, I'm not even sure.
Not.
So,
yeah,
like 3 to 100 nodes, not something I would recommend doing, or the opposite. So it's just like, it might be trivial to scale, but you still have to put some thought into it. You want to bring a node in one at a time. You know, you don't want to. You want to wait till all the transfer, the data transfer has taken place and the cluster is settled, and then you want to bring your next node in. Just don't go crazy. Like, oh, join. Fun. It's good when you have no data and no throughput, like going on, no load at all. It's great, but when you're in production, it's a totally different story.
So what kind of monitoring tools do you have? Maybe that's next.
That's a good question. But in the open source version, there's a stats resource. So /stats, you just query that, it'll give you some ideas of what's going on. There's also a log, and there's a lot of work going on with that stuff as well.
No, I was just trying to say, like you just said, wait till everything's settled.
Yeah, you can.
How do you tell?
You can basically watch from the console, from the React console. You can see the log messages, and you'll see like when handoffs are done and whatnot. The other thing that ops love with a distributed system like this is that it is linearly and predictably scalable. I said that at the beginning. It's true. This is actual. I mean, I didn't just like open up numbers and start drawing numbers. This is, or drawing, plotting random points. This is actually from a test that we ran. If you want to read about it, it's here. And you can see that basically a node would handle about 1,500 or 1,800 requests ops per second, and that happens for each node, per node. And it's completely linear. So as I add capacity, I can predictably scale up as well in terms of throughput, in terms of the ops per second that I'm actually doing. So it's boring.
Is there a maximum limit to this? I know at one point Erlang had some maximum.
It's not really a limit imposed by Erlang. It's more kind of a limit imposed by the size of your network and like how large can the ring get before like networking starts to break down.
Right. Also, traffic starts to add up at that scale. At several hundred nodes is where it starts to be problematic.
Thank you. Yeah, like what we've noticed is like around 200 to 300, it starts getting fuzzy. So.
But that 200 to 300 8 gig machines, how many?
I would recommend, and a lot of times what I do is I recommend people scale up their machine. Like if you know, an 8 gig machine is, I mean, that might be commodity at this point, but it's still pretty dinky compared to what you can actually get. You know, we have, some of my favorite implementations are all on like 96 gigs of RAM, you know, like RAID 0 SSDs, you know, sexy stuff. So,
how well does it handle heterogeneous clusters of machines if you have some 8 and some 24? How does it?
It's transparent.
But I mean, does it appropriately send the right number of partitions to the bigger, more powerful machines?
No, it will evenly divide it amongst the ring. It doesn't know.
Can you wait ring? So if I was going to bring in a new node that was bigger, can I say this one can actually handle 2?
No, you can't. Another feature that ops get is fault tolerance, and I think this is just an aspect of Dynamo, but also an aspect of Riak because we're built on Erlang. For those of you who aren't familiar with Erlang, Erlang's fairly known for its fault tolerance, and it will transparently utilize all the cores and CPUs up to a reasonable limit, and you'll basically be able to use the hardware you paid for. So I'm a big fan of Erlang. Ask Travis. You get data replication, so you know that your data is kind of safe. You have no single points of failure. So these things are just aspects of Dynamo in general, right? Your cluster can transparently survive failures and network partitions and split brain and whatnot. And I think what we're thinking about when we're building Riak is how do we make your data super safe? Like you're not going to lose it. It's durable. Like it's always going to be there. You can count on it. And how can we make sure that this shit never happens? Like 2 a.m. Servers on fire. Like no big deal. Actually, there's a great story that our CTO tells. When they first developed Riak, they were actually running it in a production app. And they had a 5-node cluster, and they got a call like in the middle of the night from their data center, basically saying, hey, like you guys just lost 2 nodes. And they were like, okay, we'll deal with it in the morning. And they were like, what? Yeah, so it's just like, it just allowed them to like handle the call and be like, hey, don't call me this late. And hang up the phone and then deal with it in the morning. What users get with Riak is this. And this is basically one of our benchmarking tests. This is actually one of the benchmarkings that I showed you from the dots and the lines going forward that I didn't make up. And basically it shows you, this is a 5-node cluster on Joint. It's running about 7,000 ops per second. This is an older version of React too, so it might be a little bit more performant at this point. Your average request times, you're at 2 milliseconds, under a millisecond. You can see that they ran this for a few hours when they did this test. This is your 99th or 95th percentile. They were getting 3 millisecond latent requests and handling this many ops on a 5-node cluster. And these are 4 gig machines, by the way, of RAM. And then somewhere around in the 99.9th percentile, somewhere around like 50 milliseconds for a request. So I think actually this is a really good example of how low latency data at scale is being solved. And so again, meanwhile I'm back at Basho. What we're doing to stay in business is that we have an enterprise product. All of the stuff that I've talked about is basically open source. It's completely available. Go ahead and use it. Rock on. We have, I think, something like 60 open source repos that we maintain on our organization on GitHub. We're pretty proud of being an open source company, first and foremost. The pieces that we try to sell are the pieces that really we think that only enterprises need, and that they should have the money to pay for. So one of the first things is support, and I really like to think that we have support that we can brag about. Almost everybody in our company, I'd say and the number's shrinking because we're bringing on some sales and marketing people, but almost everybody is a pretty hardcore engineer, has done something kind of interesting in their life, or is doing something interesting, or has some kind of past history with an interesting project. Pretty hardcore developers. Our support team is all made up of developers. When you call our support team, you get somebody on the phone who knows the product inside and out, which is pretty awesome. I really hope, we strive hard to maintain that level of support as well. We're not just hiring people who don't know what they're talking about. It's a pretty intensive process. A lot of the guys are Erlang programmers, sysadmins. Sean Cripps, I mentioned earlier, does the Ruby library. He's part of our support team. So we call them developer advocates. They are developers. We have multi-site replication, SNMP, JMX monitoring. So if you have a NOC, you want to plug it all into that. And we also have a web UI, but that's hardly not our selling point, trust me. It's really these pieces above for the enterprise. And really, the bread and butter for us is our multi-site replication. And the way that works is it's not just one big ring around the world. What we do is actually duplicate ring state from location to location. And mind you, I chose the US. I first chose the world, but then I had to make the rings really small and they just looked really stupid. So I just had to turn up the resolution a little bit so that I could actually make a better slide. But we definitely have implementations that wrap around the earth. And basically the way that our replication works, and I like to talk about it because I think it's pretty cool, is that the cluster will elect a leader. And that leader will maintain a first in, first out queue. Every time an object's written to the cluster, it's put on the queue and it's sent over unidirectionally. That's why I have the single arrow to whatever cluster that you point to. And you end up with basically a cluster of clusters. You can do that bidirectionally. You can do it all sorts of different ways. I've seen some pretty interesting configurations in terms of these clusters of clusters. It really is for those who are truly obsessed with low latency data, like they want to be at the edge of the network. They want to be, that last mile close to their user and being able to service responses. It's also for those who are extremely paranoid, who really, really are concerned about their disaster recovery story. And one of the things that I found as I've been dealing with enterprises, talking to them about Riak, is that a lot of them have always thought in terms of disaster recovery. Like, hey, what's my backup plan? Like, what am I going to do like once this place fails? Like, how am I going to bring it back live or whatever? I'm starting to think that instead of disaster recovery, it's really disaster survival. Like, hey, you don't have to go down. Like, it doesn't have to be the end of the world for you. You don't have to recover from this. You can survive it. And this is the kind of plan that allows for that.
Can those elections, when the clusters are electing a leader, can they get hung up trying to figure out whose leader's going to be?
No. There's actually a behavior knurling that provides for that. Works out pretty well. It's kind of, they're good at it. And if that leader, for some reason, like catches on fire and that node blows up, it will actually go ahead and say, oh, we lost our leader, and it will go back through the cluster and elect another leader.
Is there ever any need to have a node that's specifically an arbiter?
There is nothing like that in Riak at all. There's no special node. It's a completely decentralized distributed system, which then gives you no single point of failure.
So in that case, what happens to the queue of pending writes?
Yeah, good question. So it gets dropped. And if that's the case, what we have is one other mechanism that takes place. And it's basically, we go through, we create this Merkle tree, and it's a hash table with all the different hashes of the objects. And the ring goes through, creates this great big Merkle tree, and sends it over to the other ring. The other ring does the exact same operation, does a diff comparison, sends it back to the primary ring, and the ring goes, okay, you need this shit. And so we start streaming it again. And the way that happens is it happens on by default, we've defined it to happen like every 6 hours. You can completely configure it however you want. It's an expensive operation to perform on the cluster. But by default, we have it configured for 6 hours, and we also have it configured for whenever your link flaps. So like if the link flaps, it will start a full sync again, because it knows what happens is that queue just disappeared. That queue also is basically an in-memory queue and is adjustable. So however long you want to adjust it for whatever kind of data that you're sending, what your throughput rates are like. Eventually, you can only put 10 pounds of shit in a 5-pound bag, and if you're sending so much through, things are going to fall off the back of the queue. And in that case, the full sync is there to pick it up. And also the configuration option for the network flapping to kick off a full sync, what we call a full sync, that's also configurable. So like, again, the full syncs are an expensive operation. If you don't want it to happen because your network flaps all the time, then you can turn that off, and you can kick it off manually, you can pause it, you can restart it.
So is there no way to block on replication in another data center?
What do you mean?
Like when you do your put request, can you block on replicating to outside the data center?
No, you cannot. Yeah, no, it's truly state replication from, ring state replication from location to location to location. So I figured I'd highlight some of the users of us, and these are customers, not just users. These are some of the guys that have found value in our enterprise services so far, and pretty proud of this list. And there's actually a handful of here that I can't show you, which kind of I really want to, but I can't. And so these guys have found all really interesting, cool use cases for Riak. Which mainly what I found as good use cases are like things like session storage, file system. Like you want to treat it like a distributed file system, go for it. You want to use it as a cache, that's perfectly acceptable. Go ahead. Like I know people who are getting sub-millisecond latencies.
Do you mean actually storing binary content?
Absolutely.
For the file system?
We don't care. You can store whatever you want. That's kind of like, and there's some trade-offs. Like with Cassandra, like you actually have some options that if you want to do like time series data, like Cassandra does that fairly well compared to what Riak does. And that's because of your column table families and stuff like that. We don't do that because we're content agnostic. We're just a key value store. We're just going to allow you to dump your shit in. User profiles is another one that I've seen a lot of people doing. Account profiles and stuff like that. That's pretty common. They want to be able to have the user profiles geographically anywhere. And also activity streams is something that I've seen people successfully do. Yammer's doing it. FormSpring is also doing it. Here are some things that I think aren't exactly unicorns and rainbows. Time series data, I would not recommend doing it. Although I should say that in 1.0 we're going to make, the level DB will probably, they haven't ordered keys. It will give us some, it'll inch us towards it, but it's still not, it's not like the greatest thing in the world for us. Analytics right now, I'd say stay away from. If you're going to do anything like Hadoop style, stay away from Riak. It's not our bag. You'll be sorely disappointed and you'll curse our name forever, and I don't want you doing that. That again, 1.0, we're doing some things with our distributed computation that should help alleviate that in the future, and you will be able to do long-running requests and querying for data, and so things will hopefully get better. Things that we probably aren't thinking about at all right now are things like geospatial. We'll leave that to other companies, and highly relational data. Like we have links, which are nice, but it doesn't mean that like I can go tell you exactly what's happening in zip code 33133, with 18 or to 25-year-old girls. Trust me, I really don't know. And like I can't slice and dice data however I want. If you want relational data, like you're better off with a SQL data store. With 1.0, which is coming up about Q3, like maybe in September, October timeframe. Yeah, sometime in there. We're going to be releasing secondary indexes, indices, whatever you want to call them. And that's probably the main key feature. Right now, I've seen people do some really weird things, basically maintaining their own indexes. It's kind of a pain in the ass right now. But we are now going to be enabled into that. So if you want to look up by email address and user ID, totally possible.
And that's going to be fully distributed, so no single point of failure for those indices?
Correct.
Okay.
Let me think. What else? Yeah, the distributed computation framework that I was talking about. Basically, our MapReduce, we went and rewrote it. And so now it has, now it's built, it's called React Pipe, and it's basically modeled after the idea of Unix pipes, but through the Dynamo system. It's basically Unix pipes for Dynamo. And then we've now layered our MapReduce system back on top of that. So then you can pipe jobs through, and it will distribute it around the cluster. React Search, as I mentioned, is going to be merged into the core product. It's going to be one and the same. React Search right now is different than our React KV. And they are now going to become one. So that's super cool. We're going to be introducing the LevelDB backend, which is the new backend KeyValue file system file storage option from Google. We're doing a lot of things around UX because one of the major complaints we heard from our users was, I'm not an Erlang programmer, and everything's like, Erlang SASL logs, and you really need to know what you're looking at. For me, I'm like, oh, okay, I get it. But for other people, no, not so cool. Some other things that we're working on is better ring claim ownership, or ring claim, and partition transfer. When physical nodes are added and leave the system, added and subtracted from the system, we've worked on making that a more efficient, more effective. As Brett knows, there are times when you can tell a node to leave, or partitions are being transferred that you basically get objects that are not found, even though they really are there. And so we've put a lot of effort into resolving that problem. In fact, I just saw the commits today for it. So it merged into master, so I'm pretty stoked about that.
Can I run master yet?
Yeah, yeah, you can run master, but not in production.
That's what I meant.
You can run it in production,
run
though. Don't call me. And then also we're going to be adding primary read and write control, which basically means that you can guarantee that there are primary nodes that have accepted your data. And a unique number of those primary nodes, not just the partitions in the ring. All right, so I'm going to end with what I think is the truth, which is distributed systems are hard. They're not easy, I promise that. Low latency at scale is hard. And this, I think database vendors should strive to make these trade-offs that exist clear. If they are not telling you that there are trade-offs, then they're lying. And so I encourage you guys to all know the trade-offs that exist in the solutions that you choose. And the best way to learn what the trade-offs are for Riak is to get involved. We have a mailing list. It's not crazy active. It doesn't blow up your inbox, which is great, but it's definitely enough that you can begin to grok what we're about. You know, like I said, we're an open source company. Everything we do is ASL v2. If you want to contribute back, we totally accept that stuff. Any questions?
I've got a few.
Yeah, sure.
We can begin. So one thing that I guess there's Cassandra guys as well. So I'm kind of like thinking about things I've heard about Cassandra and what you presented. So I'm thinking about the tunable consistency. So there was a while when Cassandra was kind of saying, hey, we're the only ones that are doing this, and now you guys seem like you've offered something. But I was kind of getting the idea that your tunable consistency was a little bit more runtime with the requests.
They are.
And is Cassandra
They're the same.
All right. So
Cassandra and Riak are very, very similar products.
Yeah, I was just trying to figure that out. Okay. So the next question is, if you say write with this level of replication, right? It seems to me like that is, how would you go about undoing that level of replication?
You would change what are called the bucket properties. You can do that with a request.
Okay.
And then the ring will gossip about it, what the changes are in the configuration.
So the ASHA is rich enough to support that?
Yep.
Okay, gotcha. And the other question was, you maybe confused me slightly because I don't know enough about what your MapReduce is. So like I'm thinking MapReduce, I'm thinking about going off to all the virtual nodes and running this computation, and then all of a sudden like I can't help but think of an analytic when doing that for anything. So I'm having a hard time understanding what kind of thing that MapReduce would be good for.
Yeah, okay, so our MapReduce isn't good for data processing at this point. And I would probably wait for React Pipe to mature a little bit more, which will be part of 1.0. It's on master now. What Riak's MapReduce is good for now is very ad hoc queries. So like if you're maintaining your own indexes, which are a lot of people are doing right now, this works pretty well in that case. You have a targeted set of keys that you're going to map over.
Gotcha.
So I might have 1,000 keys. You know, a good example of the way that it works in Riak is the links feature that I talked about earlier uses the same MapReduce. It's an Erlang MapReduce call. And what it will do is then take your metadata, it sees that, hey, I have links to all of these other related objects. I'm going to go out and map these functions across and start transversing and then reduce and pull it back and send a response back.
So in your, what kind of indexes do you think most of your customers are using when they do that offline? I'm just asking for technology just to see what they're marrying with.
Well, so like, what kind of indexes are they? And it really just depends on what their use case is, but like in an activity stream, they might want to index for a user, or another good example is they might actually create an object just for, like, I want to index by email address, but I also need to keep it, but I'm going to keep the information for them by a particular ID, a particular identifier. So they have to create a whole other object, and then there's a relationship between that. Maybe they have multiple email addresses. And
well, actually, you are answering my question. So the answer is that they're kind of doing the pseudo-indexing within Riak,
yes.
Not necessarily something offline.
Right, correct.
Cool. Gotcha.
Yeah, sorry.
So they're doing it with the links?
Either they're doing it for links or they're actually maintaining their own, like a list of like other identifiers, which actually a lot of people are doing just as much.
See, with the secondary indexing, it's associating multiple key.
I really don't know much about secondary indexing yet.
Yeah,
Ask too many
I mean,
questions.
obviously the primary index is the key, and then there's only a single value. Yeah.
Yeah, you know, there's a really great presentation. I haven't played with the secondary indexing at all.
I can tell you a little bit. For secondary indexing, you have to set it in the metadata. So yeah, the blob is still opaque to React, but you could say age 25,
And that's in the
in the
metadata.
metadata, and then that's indexed.
That makes
So-
sense.
And you can have types in there, ints, strings, and stuff like that. So you can do less than, greater than, all that kind of shit.
So it's basically key values that are indexed in the metadata, but you can add arbitrary key values to it.
Yeah, I guess.
That's all I got, I think. Any other questions? Yeah.
Can you query a key range?
No. Not with secondary indexes, you will be able to. Right now, not really. No.
Will key filtering work the same way in secondary indexes?
Key filtering will probably get deprecated in favor of secondary indexes. Key filtering is a little bit of a mess. I mean, it's not a mess. It's not the best option. It uses list keys, which is a really expensive operation in Riak. So I wouldn't really recommend it. In fact, that's usually when I start asking people like what's their implementation plans. If they're using, like there's a key filtering and list keys, if they're using either one of those, you know, I have to dig into more of their use case. Like how big do you plan on getting? Because those are some limiting factors. And while list keys is not going away, the list keys operation, it got a huge refactoring as part of 1.0, and that's merged back in, and much more performant. But key filtering, probably over time will be deprecated.
Can you explain those two features just?
Sure. List keys is like, hey, I have a bucket, and I want to get all the keys back. Seems like a pretty reasonable thing to do, right? You know, give me all the keys. Well, it's an extremely expensive operation. Buckets are just namespace. It has to go over the, it's like, even if I have a bucket that has 3 keys in it, it has to go over the entire data set. So if I have a bucket with three objects in it, and then I have, you know, another bucket that has millions, it's going to be painfully slow. So the good news is, like I said, it got a huge refactoring. Things are much more performant now. One of the ways that we tried to mitigate that issue was like, hey, I want to just filter, and I want to filter on this, like on the server side rather than do a list keys, come back, filter it out. We moved the filtering to the server, and that's the keys filters that he was talking about. Still does a list keys, doesn't have to stream back all of the keys. It can filter as it folds over the keys and then send back the response. Hopefully that'll get no longer needed because you'll be able to maintain secondary indexes.
Question on the large object storage you were talking about?
Sure.
So it chunks it up, and each one is stored as a separate thing, right?
Correct.
And replicated.
Correct, object, yeah.
Is there anything special in there to deal with the possibility that if you have a less than quorum read and write, that you get eventually consistent chunks back, like pieces of, this chunk came from this consistency and this chunk came from another writer? In other words, what you get back didn't have all the same pieces that you put in.
Right.
Is there anything special to?
So, as far as I understand it, the tree that's maintained will maintain the vector clock IDs or the identifiers. You shouldn't have inconsistent chunks.
So in that case, like
because there will be different keys. Like if I write the object again, the chunks will be different keys internally.
Gotcha. Okay.
So in the question about the VNode partitions again. So in the images, at least you showed the same pattern of physical nodes, owning partitions.
Mm-hmm.
Do you assign partitions randomly, sort of, to physical nodes, or is it always like a round robin fashion that you assign them?
That's a good question. We'll pull that up. I guess this is the best assignment
Yeah.
slide. So we do it round robin. And we changed our claim algorithm. I mentioned that it just got committed to master today. I haven't looked at what the actual specification is for it, but as I currently understand Riak, the way it's currently implemented is that it's round robin. It's basically striped across the cluster so that it looks a lot like this. So I go 1, 2, 3, 4, 5, and then just take the partitions and go around and just keep going around round robin.
Just for point, just so I know, what does Cassandra do?
It doesn't have
They don't
virtual
have V nodes. The node only has one part of the ring. But how do you add nodes then? Like,
Physical nodes?
yeah. So when you add a physical node, there's a set number of partitions. So you
Right.
just take a partition from all the other nodes.
Yeah, it's just it will repartition the ring for the new node to claim. I'm sorry, it won't repartition the ring. There's still always 32 nodes, or in this case, 32 partitions. It will reassign ownership.
Okay.
So it's basically I'll insert a whole new color, and then I'll do the round robin basically.
One big advantage for Riak here is that when you have like a 5-node cluster and you add one node, it actually, you now have, each node has 1/6, where in Cassandra you have to give it like a slice of the ring. So you have to, they generally double 4 to 8 or something like that if you want to keep your performance consistent.
Right, or manually balance.
Right, yeah, we do, basically I would say the big difference between Cassandra and Riak in terms of Dynamo, or I guess in terms of the ring, is that you guys have to manually balance the ring, right? And we do it programmatically. And there are trade-offs with both.
Right, so like one thing, when you add a node, does it stream data from all the other nodes?
It does, yes.
If your replication factor I guess it can't be higher than n, can it?
You can, but it just, what it will do is it'll end up on, you'll have replicas on multiple physical nodes. Okay. It's stupid, right? But I mean, you could do it. We allow you to shoot yourself in the foot.
Just leave meters. But you said the number of readers were fixed to number of nodes?
I'm sorry?
The number of readers were fixed to number of virtual nodes?
The number of concurrent reads on a physical node.
I'm sorry.
The number of concurrent reads on a physical node are fixed to the partition, fixed to the node count, virtual node count.
It has to do with reads being blocking for writing nodes.
So if if there's multiple vnodes, like if there's 10 vnodes on a physical node, so I'm sorry, you're gonna, and then you do a read, in theory, you should have one of those partitions for the physical node, like assigned to that. And you can certainly have 2 partitions on the same physical node, but the only thing that's blocking is the V node, not the actual physical node.
Are you limited to, so you've got 10 V nodes, are you limited to 10 reads on that physical node while those are blocking? Like if the 11th one comes in?
Yes, I'm sorry. Yes. So if they're all reading, then yes.
So by necessity, as you scale the cluster out physically, then you go down to read availability.
I believe so, that would be true.
But you set your V nodes. To be clear, like you can set that number really high.
Right.
Sure.
It's still like you have a probability of blocking for another read even if some of the V nodes are not active.
Yeah. You said you recommend like 20-ish per physical machine, right? So
right.
I don't know.
And the blocking time is only for it to read off disk, as I understand it. So
right. Yeah, the physical hard drive can't read.
Right. So I don't think that. I don't know. I don't know enough of the actual vnode internal implementation to unfortunately answer your questions.
Oh, so.
Something I don't think you mentioned, just for people that might be new to Dynamo, and I think Cassandra does this as a 08 also, is for upgrades. You can just drop the machine, upgrade the package, and bring the machine back up, which I think is like.
Yeah, that's actually a really good point. I didn't even think about having that. But you can do what we call a rolling upgrade. I don't know how Cassandra does it, but you can take one node out, upgrade it, and then bring it back in, and just go around the cluster and do that. So it's not like, again, zero downtime.
Any other questions? Thanks, Ron.
This is like my personal status.